This example is taken from a project in which screening of a diverse library resulted in hits from multiple chemistries. Without the resources to follow up all of the hit chemistries, the project team wished to focus on a small number of series which were most likely to yield high-quality leads with appropriate physicochemical and ADME properties. In the following steps, we will compare 3 virtual series resulting from expansion around these hits, using predictions from in silico ADMET models and probabilistic scoring to prioritize them for further exploration. After starting StarDrop, go to the File, Open menu item, open 3 files, Series 1, Series 2, and Series 3, representing 3 different chemical series in which active compounds had been found. You can open all 3 datasets simultaneously by selecting the files while holding the Control key, and then clicking Open. You will note that none of the datasets contain compound structures for confidentiality reasons. However, a range of physicochemical and ADME properties have been predicted for each compound. We're going to use a multi-parameter scoring profile defined by the project team to prioritize these chemical series, so change to the Scoring tab in StarDrop. Click the Open Folder button to load a new scoring profile. Select the file Project Scoring Profile and click Open. The scoring profile, defined by the project team for this project, will be displayed, showing the criterion for each property and the importance of the property to the overall objective of the project. Select each of the 3 datasets in turn from the View menu and run the scoring profile on each using the arrow button on the Scoring tab. Some of these datasets contain approximately 1,000 compounds, so we will now use some of the visualization tools in StarDrop to help us to explore the distributions of properties and scores for these different series. Change to the Visualization tab in StarDrop and choose the Series 1 dataset from the View menu. Select the column containing the score by clicking on the header labeled Project Scoring Profile, and click the Criteria Histogram button in the Visualization tab. The criteria histogram shows the percentage of compounds in the dataset that meet the ideal property criteria, as defined in the scoring profile. A high bar for a property indicates that the majority of the compounds in the dataset meet a criterion, while a low bar indicates a consistent issue across the dataset. The colors correspond to the key in the scoring profile, and the bars are ordered from the most important on the left to the least important on the right, as defined in the scoring profile. Click on the Detach button in the Visualization tab to create a free-floating copy of this plot. Untick the box next to Series 1 in the key below the plot in the Visualization tab, and tick the box next to Series 2 to plot a criteria histogram for Series 2. Click on the Detach button in the Visualization tab again to create a free floating copy of the plot for Series 2, and then repeat the process to plot a criteria histogram for Series 3. From these simple profiles, we can see that Series 1 and Series 3 both contain a reasonable proportion of compounds that are likely to meet each of the property criteria. The most consistent issues in Series 1 are likely to be high plasma protein binding and inhibition of the hErG ion channel. For Series 3, the most consistent issue is predicted to be high plasma protein binding. However, all the compounds in Series 2 fail to meet several criteria including solubility and log P, which are 2 of the most important properties. This indicates that Series 2 is very likely to be a high-risk chemistry. Furthermore, in a chemical series where all the compounds have poor values for a property, it is likely that the issue lies with the common scaffold of the series, because varying the substituent groups does not affect the outcome. From this simple analysis, Series 1 and Series 3 look to be the most promising. However, it is difficult to confidently choose between these chemical series. To help us to explore these chemistries further, we will use the snake plots generated by probabilistic scoring. On each of the detached plots, click on the snake plot button to change the plot type. A snake plot shows the compounds in a dataset ordered along the x-axis, from the highest scoring on the left to the lowest scoring on the right. The score for each compound is plotted on the y-axis, and an error bar around each point shows the uncertainty in the overall score, given the uncertainty in the underlying data used to calculate the score. From these snake plots, we can clearly see that there are compounds in Series 1 that have a high chance of meeting all of the property criteria, indicating that this series is most likely to yield a high-quality compound. Resources should be focused on following up this series and generating experimental data to validate this predicted hypothesis. Although the criteria histograms suggest that Series 3 appears to meet more criteria overall, most of the compounds in this series have poor predicted absorption, which is one of the most important properties. Furthermore, those that are predicted to be well absorbed are unlikely to meet other criteria. This results in a lower likelihood of success than for Series 1. However, given the uncertainty in the data, as illustrated by the error bars for the highest scoring compounds in this series, it may be worthwhile sampling a small number of compounds and generating experimental data as a backup strategy. Finally, the snake plot for Series 2 confirms the picture we saw from the criteria histogram for this series. The chances of success of the compounds in this series against the profile of required properties are very low. Furthermore, the confidence in these assessments is high, as indicated by the small error bars. This is because the chance of all of the models being incorrect simultaneously, resulting in an unexpected success, is very low. This example illustrated how we can rigorously compare three chemical series by assessing their properties against a profile required for a successful compound in the project for which they are intended. By taking into account the importance of each property to the objective of the project and the uncertainty in each prediction, probabilistic scoring can quickly and confidently identify the chemistry with the highest chance of success. To download the example files and step-by-step guidelines to try this example yourself, visit the tutorials section of the Optibrium community.